In this video, we're going to take a look at cast diagrams and solving trigonometric equations. Now, when we're solving trig equations in A-level maths, there are two methods in particular that are useful. The first method is a graphical method, and the second method is a cast diagram. And what we're going to focus on in this video is a cast diagram. So let me just write this down here. So a cast diagram is a great tool in solving trigonometric equations. So how do these work? Well, what we do to begin with here is we draw four quadrants. Okay, so in other words, just draw an XY plane. So what I mean by that is your regular Cartesian plane. Don't have to be perfect, but just something that looks like this here. So you can see you've got your four quadrants, quadrant 1, 2, 3, and 4. And we use these four letters here to help us basically decide where the trig functions are positive. So you might think that this is the first quadrant here, or with this being the first quadrant here, that C would go here, but it doesn't go here. So C begins here, then A, then S, and then T. Okay, so the C here tells us that cosine is positive in this quadrant. In this quadrant here, the A tells us that all the standard trig functions are positive in this quadrant. This quadrant here tells us that sine is positive, the S stands for sine. And then finally, in this quadrant here, the T tells us that tangent, or tan, is positive in this quadrant. Okay. So let me just pick a very basic example here. Let's say that we have cos x is equal to a half. Okay. And what we're going to do here now is solve this trigonometric equation using our cast diagram. But before we kind of do that, let me just quickly illustrate how the cast diagram works. So when you solve a trigonometric equation here, okay, what we'd normally do here is take cos inverse of both sides. And in that case here, what I'd get then is x equals cos inverse, or arc cos, whichever you prefer, of a half. We'd then just simply put that into our calculator, or just use the exact trig values if you need to. And in this case here, what we would get is 60 degrees. Okay, we get 60 degrees there, right? So what we call this here is our principal solution. Okay, and the principal solution goes in this quadrant here. Okay, so my 60 degrees is there. Okay, now when we work with a cast diagram, we start on this line here. Okay, and we go counterclockwise or anti-clockwise, whichever you call it. Okay, we're going to go around this way. Now, because we're working with cosine here, we need to consider where cosine is positive. Well, seeing as all standard trig functions are positive in this quadrant, that's obviously where the principal solution goes, so that's the 60 degrees. But where else is cosine positive? Well, that would be this quadrant here. Okay, so that 60 degrees would also be here. That's also 60 degrees. And the same is true here for the other quadrants. So this angle here would be 60 degrees, and then this angle here would be 60 degrees. Okay, but for the sake of this question, we don't need these two. Okay, so what I'll do is I'll just eliminate those for now, but we will come back to that idea in a moment. Okay, so let's get rid of those. So now with the cast diagram here, like we said, we start at this line and we keep going round. So my first solution here, we start here and touch this line, that's 60 degrees. We already know that, that's our principal solution. However, how do I get my next solution here? Well, let me do this in a different color. Let's do it in orange. So again, we start at this line and we go around and we keep going until we touch this line here. Okay, and what I'm looking for here now is this angle that's found from here all the way around until we touch this line. Okay, so how would we find this here? Well, just think about some basic properties of angles. So if this angle here is 60 degrees, one full revolution, so one turn all the way around, would be 360 degrees. Angles are in a point. However, we're going to this line here, so x in this case would simply be 360 minus this angle here of 60, giving us 300 degrees there. Okay, so this would be now if I'm solving between, say, 0 and 360 degrees. Okay, those would be my two solutions there, and the question would be complete. Okay, So there's a few things to also consider here. The range of our solutions here can change. So what about if my range was, say, 0 to 180 degrees? Well, if this were the case, we would have to omit this solution here, okay? Because 300 is larger than 180, it falls outside of the range that we accept, valid solutions for. So in that case, we wouldn't include the 300. You might also have a larger range. So for example, let me just do it underneath in a different color. Let's say you had 0, x between 0 and say 720. What would we do in this case here? Well, in this case here, what we'd have to do now is consider the periodicity of our trigonometric functions. Let's just make this point here now as well. When we talk about periodicity, what we're talking about here is when these trig functions repeat. So we say that sine and cos are periodic every 360 degrees. Sine and cos are periodic every 360 degrees. And then for tan here, or tangent, tan is periodic every 180 degrees. And what do we mean here when we say periodic? Well, what we mean here is that it just repeats every, say, 360 degrees for sine and cos, and then every 180 degrees for tan. Okay? And why is this important? Well, it helps us obtain the further solutions. So in this case here, once we obtain these two solutions, all we need to do now is consider what happens when we add 360. So if I've got 60 and I add 360 here, that would give me 420. So my solutions here would be 60. I would have 300. I'd then have 420 because 60 plus 360 is 420. And then I'd also have 300 plus 360, giving me 660 there. Obviously, if I now add 360 to 420, we're going to be larger than 720 here. So we fall outside of the acceptable range of valid solutions, essentially. So we would omit any further solutions. Okay, so like you can see, the range of solutions changes depending on the initial range here for the variable that we're solving for. In this case, x, but usually we would use theta to represent that angle. Okay, like we said, important to note here, sine and cos are periodic every 360 degrees, and tan is periodic every 180 degrees. Do make a note of that, very, very important. And then finally, if I just go back to the cast diagram here, just to help illustrate this idea. So I just draw my quadrants again here. I've got C, A, S, and T. So, like we said, our first solution here in this quadrant is our principal solution, which we note here as x. Okay, so in this quadrant here then, going from here to this line, if this angle here is also x, then from here to here that would be 180 minus x. 180 minus x there, because one full turn from here to here is 180 degrees. Angle's on a straight line. I want to get rid of this angle here. Okay, so we subtract x. We've now got t here. So again, I've got this angle here. So from here, this would be 180 plus x, because we want this angle as well. That's 180 plus x. And then finally, like we saw here when we solved for cosine, this would be 360 minus x there. Okay, we've got x here again. So there you can see this is a relatively straightforward process. And that was for tan. It's a relatively straightforward process. It just takes a few examples to kind of get this process down, understanding when, which quadrant we're working in, when we, for example, subtract, when we add, when we subtract again. Okay. But that's everything that we need there to get started with cast diagrams and solving trigonometric equations. So now let's take a look at some practice questions for cast diagrams and solving trig equations. Starting off then with the first practice question here on cast diagrams and solving trig equations. For this question, we're asked to find the solutions of the equation sine theta equals 1 in this given interval here. So where do we begin here? Well, if we just take a look at the equation here, so sine theta equals 1. With this equation, there's nothing on the side here of sine theta. So in this case then, I can go straight into taking sine inverse of both sides. So if I take sine inverse of sine theta, I simply get left with the variable that we're solving for here, in this case theta. So therefore theta is equal, then on the right hand side here would be sine inverse of 1. So sine inverse of 1, that is 90 degrees. Okay, so put this into your calculator here, and you should get 90 degrees. Like so. Okay. So once we get our principal solution here, so this is our principal solution, once we obtain this, what we need to do now is draw our cast diagram. So it never has to be perfect. Just draw 4 quadrants here. I'm doing mine freehand, so it's not the neatest. We get something that looks like this. That's absolutely fine. Okay. Remember, we start with C down here. That's for cosine. A in the top right for all trig functions. S here. And then finally, B there. Okay, so cosine, all, sine, and tan. So our principal solution goes here. Now this one's a little bit different because the actual principal solution that we've obtained here is 90 degrees, so it's a right angle. Okay. If I was to draw this line going out here and calling that 90 degrees, I personally couldn't do that, right? That's not correct. It is clearly perpendicular. So let me just draw that in as a square. Okay. So my principal solution is from here to here. Okay. And in this case, that would be 90 degrees. Okay. So where else is sine positive? Well, sine's also positive in this quadrant here. Okay. We're working with sine here. And then obviously, like we said, sine would also be positive in this quadrant here. So for our second solution then, remember what we do here is we normally go around like this until we get to this line here. So that would be 180 degrees, angles on a straight line. And we subtract this angle here. Okay, but clearly if I've got 180, I subtract 90, it's just taking me back to this line again. So in other words, I'd again get 90 degrees. Okay, what that tells us then is we only actually have one solution in this given interval here from 0 to 360 degrees. And that solution is theta equals 90 degrees. So therefore, let me just write this down. Therefore, theta is equal to 90 degrees. Now we don't need to worry about adding 360 degrees here. So remember, sine is periodic every 360 degrees. But we don't need to worry about that because my given range here is from 0 to 360. If I add 360 to 90 degrees, that gives us 450 degrees. And obviously we fall outside of the valid range here for solutions. So we wouldn't include any further solutions like that. That just gives us the one solution there. Theta equals 90 degrees. And that gives us the solution there to question 1. Moving on to question 2 now, we're asked to find the solutions of the equation 2 cos theta equals 1 in this given interval here for theta. So if we just start by taking a look at the equation here, because it's 2 cos theta rather than just cos theta on its own, we can't take cos inverse yet of both sides. I need to get rid of this 2 here in front. So because we're timesing by 2, I'm going to balance this equation by dividing both sides by 2. What that means then is we get cos theta here is equal to a half. Okay, 1 divided by 2 gives me a half. And now, because it's cos theta on its own, now I can take cos inverse of both sides. So if I take cos inverse of cos theta, I simply get left with theta. So theta here is equal to cos inverse of a half. Okay. So cos inverse of a half here, what we need to do now is just put this into our calculator here. And if you do that, what you get is 60 degrees. Okay. And remember, this represents our principal solution here. And what we're going to do now is draw our cast diagram. So if this is my cast diagram here, get something that looks like this. This is C, this is A, this is S, and finally, this is T here. So our principal solution goes in this quadrant here. That's 60 degrees. Okay. Now, where else is cosine positive? So working with cos here, like we said, where else is cosine positive? Well, it's not positive in this quadrant, that's sine. It's not positive in this quadrant, that's tan. It will be positive in this quadrant here. This is cosine. So if I mark my other line in here and this angle here, again, of 60 degrees. So my first solution, I'll just draw these in different colors just so it makes it a little bit easier to understand how this works. That's from here to here. Like we said, that was 60 degrees. That's 60 degrees there. Then for my second solution here, again, let me do this in a different color. Let's do it in blue. We again go from this line, and now we go round, round, and round until we touch this line here. And what we're looking for now is the angle formed. Well, in this case, if we were to go all the way around, that would be 360 degrees, angles around a point. However, we don't want this 60 degrees here, so we're going to subtract that off. So in that case then, it would be 360 minus 60 there, giving me 300 degrees. Okay, and there we have it. So let me just present the solutions here together. Do that in red. So therefore, our final solution here for theta is we get 60 degrees and 300 degrees. And 300 degrees there. And we don't need to worry about, you know, cosine being periodic every 360 degrees. But if I add 360 to either of these solutions, we'd fall outside the range of valid solutions. Okay, so there we have it. So that's the solution there to question 2. And finally then, if we take a look here at the very last question for cast diagrams and solving trig equations. For this question, we're asked to find the solutions of the equation sine 3 theta is equal to root 3 over 2 in the interval for theta between 0 and 360 degrees. This question is certainly more challenging than the previous few questions. And the reason for that is because the actual argument now of my trigonometric function here, sine, it's not just theta, it's 3 theta now. And this does change things ever so slightly. So the way that we start, we begin in the exact same way. So there's nothing here in front of sine, so I can just go straight into taking sine inverse here of both sides. Now if I take sine inverse here of both sides, well on the left hand side, I'd get left with 3 theta here, so be careful. This isn't just theta. In this case now when I take sine inverse, I get left with 3 theta, and that's important. So taking sine inverse of both sides, we get 3 theta is equal to sine inverse of root 3 over 2. Get root 3 over 2 there. Okay, so sine inverse of root 3 over 2. What you're going to do here is use your calculator. So if you do this, you would get 60 degrees here. So sine inverse of root 3 over 2, you should get 60 degrees. So what we need to do now is just consider something important here. The solutions that I'm finding here are for 3 theta. Now we're looking to solve here for theta. Now the original interval here is between 0 and 360 degrees. So what I'm going to do here is just change my interval to match the 3 theta. So rather than it being for just theta, I'm going to change the interval here. And what I'm going to do is just times through by 3 to get 3 theta here for the interval. So it would be 0 still. We get 3 theta. And then for my upper bound here on this interval, I'd get 360 times 3. That would give me 1080. Okay. So the reason I've done this here is just because it makes it easy to see which solutions we're going to accept and which solutions we omit. Typically, I only do this when we're, for example, the argument here is a multiple. So for example, 3 theta, 4 theta, 5 theta, something like that. If it's say theta plus 20, theta minus 10, I don't typically alter the range here. But I think it's, you know, pretty obvious which solutions would be omitted. When you're timesing like this, the solutions can get quite large. So just to keep it straightforward, I am going to edit the range here. Okay. So that's the range that we're going to work with for now. We'll edit that in a moment just to solve for theta. So where do we go from here? Well, I've got my principal solution, but what I need to do now is draw our cast diagram. So just like usual, we draw our cast diagram here. Something like this here, like so. We've got C, A, S, and T. Okay, we're working with sine here. So where is sine positive? Well, sine is positive here. That's my principal solution of 60 degrees. And sine is also positive in this quadrant here. Okay, so this solution here, again, let me do this in a different color. We start this line here, and we go around until we touch this line here. What we're looking for here now is the angle that's formed. Well, that would simply be 180. So from here to here, it's 180 degrees, angles on a straight line. We subtract this angle here. So we minus this angle here, which is also 60 degrees. In that case, then I get for 3 theta as well, I get 180 minus 60, giving us 120 degrees there. Okay, so that's our first two solutions here. Okay, so let me just write these down. So for 3 theta, do this in red. So for 3 theta, we have two solutions to begin with. I've got 60 degrees, and we also have 120 degrees here. Now, clearly, this range here is from 0 to 1080. So these two solutions here clearly won't be the only solutions. So to get my further solutions here, I'm going to consider the periodicity of a sine. So sine is periodic every 360 degrees. I'm going to add 360 to these two solutions, and then we'll keep going. Basically, we keep going until we fall outside of this range here of valid solutions. So 60 plus 360, that would give me 420 degrees there. I then add 360 to 120. So 360 plus 120, that gives me 480 degrees. Then what I do is I add 360 to this solution here. So 420 plus 360, that would give me 780 degrees. I get 780 degrees there. Then I add 360 to 480 degrees. So if I do that, I get 840 degrees. And if we just go one more time here, if I add 360 to 780 degrees, then this would give me 1140 degrees. Now clearly, we are going to omit this solution because I've now fallen outside of the range of valid solutions. And like we said, that's why I alter the range here, just so we can see basically which solutions we'll include and which solutions we will omit. So we don't include this one, so we can get rid of that. And then from here, we're nearly done now. So this is for 3 theta, but remember, we're looking to solve here for theta. If we've got 3 theta, but we want theta, all I need to do now is divide all of these solutions here by 3. So therefore, for theta here, I'm going to get 60 divided by 3, so that's 20. We get 20 degrees there. We've then got 120, so divide that by 3, I get 40 degrees there. We've then got 420 degrees, divide that by 3, and I get 140 degrees. You go in here, so 480, divide that by 3, I get 160. 2 more to go here. So 780, divide that by 3, I get 260. And then for my final solution here, we have 840 degrees. Divide that by 3, and we get 280 degrees there. Okay, and there we have it. So this is what you should get here for your final solution. So 20 degrees, 40 degrees, 140, 160, 260, and then finally 280 degrees there. And there we have it. So that's the solution there to the very last question here. That brings us to the end of this video on cast diagrams and solving trigonometric equations.